Hello, and welcome back to a video series on MAC 1105 College Algebra. My name's Sean Perry. These are guided notes number 17 in the series on Chapter 4.2, Graphs of Polynomials. Let's dive right into the guided notes. For the next few problems, we want to consider the following function, which will be a polynomial. What is its degree? Identify its constant term, if it has one. Identify its leading coefficient and leading term. The degree of the polynomial will be the largest exponent that has a non-zero coefficient. The largest exponent here with a non-zero coefficient is 9. So the degree of f is equal to 9. The constant term is going to be this right here, negative sign and all. The leading coefficient is the term of largest degree, and the leading coefficient is the 8 from this term. For the next one, our largest exponent is this 18. So the degree of the polynomial is 18. The constant term is down here at the end, 1/2. The leading term is going to be this radical 11, x to the 18, and the leading coefficient will be that radical 11. Remember, in a polynomial, we're allowed to have odd and interesting numbers up front here, like this radical 11, or this pi over 4, all perfectly acceptable. This is simply a polynomial with real coefficients. It's these exponents that are narrowly required to be positive whole numbers. This next one's a bit out of order. We can see its largest exponent, however, is this 11, not the 8 as is written up front. The degree of this polynomial is therefore 11, with leading term of 5x to the 11th, a leading coefficient of 5, and a constant term given by 5/2. Polynomials that seem not to have a constant term have simply a 0 for their constant term. Here we dig around a little to find the largest power is a 14, with a leading term given by 41.5 x to the 14, whose coefficient is indeed 41.5. Question number 5 makes use of the leading coefficient test. This is a way of describing the long-term behavior of a polynomial function. That is to say, how it will behave on the far left and right of the graph. As the name implies, we only have to look at the first or leading term of a polynomial when it is written in descending order. All subsequent terms do not matter as far as the long-term behavior is concerned. This is because eventually they are much, much smaller than this largest exponent of x. There are 4 possible situations involving whether or not a is positive or if a is negative. Likewise, if n is even or if n is odd. I would highly suggest being able to draw the following figure at will. If a is positive and n even, then just like x squared, it will rise on the left and the right. What it does in the middle is unknown and irrelevant. We're just trying to look at its long-term left side and right side behavior. Likewise, if a is negative, then this will have the appearance of negative x squared on the edges. It will go down and down when we go to the left and right. On the other hand, if a is positive and n is odd, then its behavior will resemble the cube, which rises on the right and falls on the left. Again, what it does in the middle is unknown. And again, when we take the negative of that, it flips it vertically over the x-axis and gives me the following behavior. You must be able to assign these particular behaviors to this leading coefficient, and doing that means essentially memorizing this figure or being able to tell the story that recalls it to you. Now, looking at this leading term here, we have a negative and a cube. So this will rise on the left, fall on the right. The one which does that is here. Here is our largest exponent, so this is our leading term. And we have a negative, which means this will fall and fall because our exponent is even. So where do we see something like that? Down here at the bottom. What of j? Here is its leading term. Its leading coefficient is positive, and its leading exponent is odd. That kind of behavior can be seen here and here. So this is our c. Of course, the remaining one is d, but how could we see that in this sort of factored form? Well, imagine foiling this out. Not all the way. Just the first term would be x squared, and distributing the 6x squared, and then all lower terms. We really don't need to work out the whole polynomial. We just need to see that it is a positive leading coefficient and that its highest exponent is even. that tells us it has this behavior, which we could assign to this graph. 6 to 8 ask for some similar conclusion. Considering this function, what does the leading coefficient test tell us about the end behavior? Negative and odd tell us that it has this behavior. Negative and even tell us that it has this behavior. Positive and odd tells me that it has this behavior. Here we're asked questions about degree, leading coefficient, and end behavior. Of course, the first two are essentially used to find the last one. Here's our leading term, as is this. And with this one, if I imagine partially foiling, I would get negative 13 x to the 8th and so on. I really don't much care about the lower order terms. Here, the leading coefficient is a 7, a 6, and this leading coefficient is a minus 13. We note that the degree is odd, the degree is even, and the degree even, respectively, which tells us that this has the long-term behavior of falling on the left, rising on the right, rising on the left and right, and falling on both sides, respectively. Number 12 asks, which of the following terms are interpreted as precisely the same graphical feature? This is the roots and zeros of the polynomial, which say the same thing, as are the solutions to when is f of x equal to 0. These will be precisely at the points at which the graph of the function intersects the height of 0, in other words, the x-intercepts. We're asked to assume that the above values are real numbers because if they were complex, we might have zeros which never hit the x-axis. 13 asks us to characterize multiplicity, its parity, or odd or evenness, and what the behavior of a zero is at that point. If r is a zero of the polynomial f, then f might be factored as follows, where g of x is another polynomial, and m is perhaps 1, perhaps a greater positive integer. This m here is referred to as the multiplicity, and the behavior of the graph at this x-intercept corresponding to x equals r. Notice that x equals r would make this particular term 0, which would zero out the entire function. This particular x-intercept will either cross the x-axis, or if m is even, it will come up to r and then seem to bounce off. It will touch and turn around. Now, I'd just like to mention, we don't actually know whether it will cross one way or the other. We only know that it will cross if the multiplicity is even. Likewise, we don't know if this will bounce off one side or the other. We only know that it will bounce if the multiplicity is even. This includes, the odd case includes when m is equal to 1 and when you wouldn't see an exponent here. So, in summary, if r is a zero of odd multiplicity, then it crosses. If it's of even multiplicity, it bounces off. Now, one other piece of lore is absolutely essential to understanding the following problems, and that is the sum of the multiplicities over all of the roots will be equal to the degree of the polynomial f. I'll say it one more time because it's just that important. If I add up all of my multiplicities, then I should get the degree of f, where this sum is taken over all of the roots of the polynomial f. Let's see how that logic might play out in the next problem. This one says that we have a degree 4 polynomial, and they would like us to complete this table of values. Here we can see a minus 4, 0, a minus 1, 0, and a positive 4, 0. Now, the idea is that if we didn't know the degree of this polynomial, all we would know is that this was odd, this was even, and this was odd. But as it is, these numbers must only sum up to degree 4. That is to say, this couldn't possibly be a 3, because even if this was a 2 and this was a 1, that would still sum to something greater than 4. That means these are going to have degree 1, degree 2, and degree 1 in order to sum up to have a total of 4. So our root at x equals 4 must have multiplicity 1, as must our root at negative 4. Our root at negative 1 is an even multiplicityed root, and so it must have 2, so that these will sum up to be equal to 4. All right, moving on. This graph has multiplicity 5. Here, we would normally only know that these were even, and odd, respectively. However, because the only numbers which could possibly fit in here are 2, 2, and 1, the lowest possible choices for even and odd, technically that's not true. 0 is odd, but we can't have multiplicity be 0. So multiplicities can only be positive integers. They can't be the naturals, which, in my mind, include 0. A term like x minus r to the 0th power is really just 1 when x isn't equal to r, and it's undefined when x is equal to r. So we would want to ignore things that have multiplicity 0, but I wanted to distinguish that because technically I've been talking about evens, and 0 is even. In fact, 0 can be written as 2 times the product with a number, namely 0. All right, back to the problem at hand. Because these are constrained to be so low, it must be the case that this 0 at 4 has multiplicity 1, this at 0 has multiplicity 2, and finally this one at negative 4 has another multiplicity 2. The sum of these gets me to 5, and any larger choice for these would have been greater than 5. For this next function, we're going to take advantage of it being in its factored form. We're not actually going to expand this polynomial. We can see everything we need to see right here. Namely, the zeros, or the x-intercepts of this polynomial, will be at x equals 13 and x equals positive 1. The multiplicities of these are going to be 2 and 1, respectively. And that's going to tell us that it bounces on the 13 and it crosses at the 1. The leading coefficient of this polynomial we could get by partially foiling. If I take and expand this, I'll get an x squared leading term. Multiplying by x, I'll get x cubed. And so this will at last be 14x cubed and change. I don't really care about the lower order terms. I mention this because there's one more thing we could do now that we have all this information. We could mark our zeros at 1 and 13. We know that it has long-term behavior, something like a cube. We know that it crosses the 0 at 1, bounces off 13, and continues on up to complete its long-term behavior. Moving on, all right? What is our leading coefficient? It is 6x to the 9 plus 8, which is 17, plus 7, which is 24, and change. We have zeros at x equals negative 13, x equals 0, and x equals positive 7. Its multiplicity at those zeros is, at 13, we have an 8, which is even. We have a 9 multiplicity at 0, which is odd, of course. And we have at multiplicity 7 at the root of 7, which is odd. This tells us that it bounces off the x-axis there, it crosses there, and it crosses here too. We have a polynomial that looks like a positive with even degree. So we're going to have something that rises on both sides. At negative 13, it will bounce. At 0, it will cross. And at positive 7, it will also cross. And this gives us a first kind of funny sketch of the behavior of this polynomial. With the next one, we're going to have to factor in order to see what the zeros are. So the first thing I would do here is I would pull out an x, leaving x squared minus 18x plus 81. I know 81 is a square, and the inside is twice its root. So this gives me x minus 9 squared, the perfect square trinomial formula. Now that means we have zeros at x equals 0 and x equals positive 9 with multiplicities of 1 and 2 respectively. So we know it's going to cross at this odd multiplicity and bounce at this even one. And we also know its long-term behavior is going to resemble that of a positive cube. So that's going to tell us that we cross at 0, having come from falling on the left, and at 9, we would bounce and continue then up on our merry way. Let's finish with 19. I notice 19 has 4 terms and is a cubic, so let's attempt to factor by grouping. Pulling out an x squared, we'd have x minus 1. Pulling out a 36, we would have x minus 1. And factoring this out, I'd have x minus 1 times x squared minus 36, but that's a difference of squares. So we have x minus 1 times x plus 6 times x minus 6. This will give me zeros at x equals -6, +1, and +6. The multiplicities of these zeros are all ones, which tells me that we cross at every zero and our n-term behavior will resemble the cubic. For the next few problems, we're just going to complete that analysis over and over again just for practice. So let's get underway. Here again, we have a full general cubic, and we should try at least to factor by grouping. It looks like that might yield fruit this time because I can factor out 3x squared from each of these terms, giving me x plus 4. And factoring out a -3 from this term, we'll wind up with a x plus 4 as well. So factoring by grouping will work. We'll wind up with 3x squared minus 3 times x plus 4. Now factoring out a 3, we'll have x squared minus 1. And that factors as a difference of squares. Now, setting that equal to 0 and solving, we'll get x equal to -4, -1, and +1. And our multiplicities of these zeros are all ones, all odd. So our long-term behavior will resemble a positive cubic. Our inside behavior will cross -4, -1, and +1, giving me the following graph. For the next one, we have a degree 4 polynomial with leading coefficient negative, so we will eventually have long-term behavior as such. If I factor out a negative sign, I will then have a difference of 2 squares. Factoring out the greatest common factor would also be a good idea here because I have a common x squared of both. So let's take out -x squared so we can really see our difference of 2 squares in there. Now this is going to have 3 zeros, one at x equals 0, and this difference of 2 squares will have zeros at -5 and 5. They'll both have odd multiplicity, but the 0 has a multiplicity of 2. So what we'll see is something like zeros at -5, 5, and also 0, but we will be crossing at the 5s and bouncing off the 0, which gives us something like that for our graph. I believe your homework might ask you to put, the lowest 0 of even multiplicity in, and it has a bunch of ways of making sure that you put these numbers in at the right order. I would be able to draw this picture because that's going to tell you the order of your zeros, whether or not they're odd or even, just by reading off this graph. Okay, so here we could actually factor a -5 out of both. We could factor an x cubed out of both. And what remains would be x plus 6. So if this was set equal to 0, we would have 2 zeros, one at 0 and one at -6. The multiplicities of these zeros would be 3 and 1 respectively. And our behavior would be that of a 4th degree even polynomial with negative coefficients. So it would fall on both sides. Now, we know then that this thing is going to cross at both zeros. So we would have perhaps something that looked a bit like this. It would pass right on through -6 and right on through 0 as well. And we don't know actually anything really about the wiggliness here. We only know that it does not hit the x-axis in other places. Just at 0, just at 6, and the odd multiplicity tells me that it crosses at each. Continuing on, here I could factor out x squared from both terms, and only an x plus 5 would remain. This would be equal to 0 when x was either itself equal to 0 or -5. The multiplicities attached to each one of those zeros would be a 2 and a 1, respectively, and so it would bounce off the 0 and cross at the -5. So let's mark our zeros. Let's note that our leading coefficient is positive and our degree is odd, so we're going to move the way that an odd polynomial does, falling on the left, rising on the right, and we want to cross at the -5, but then just bounce off the 0 proper, which gives us the following appearance to our graph. For the next one, I have 2 easily read off zeros because my polynomial is factored already. Perhaps x is -4, perhaps x is 1. Well, Not exactly, right? I mean, so this isn't completely factored because, in fact, this could be x plus 4 squared and this x minus 1 or x plus 1. That's its factored form, or the square root property would tell you there's two roots there. Regardless, this will also have a 0 at -1 and +1. Now, our multiplicities are most easily seen in this factored form over here, where this multiplicity is going to be 2, this one is 1, and this one is 1. Let's mark our zeros on a graph, -4, -1, and +1. Now, we know the leading coefficient of h pretty easily. If I expand this partially, I'll have an x squared up front and an x squared up front. So multiplying them together, I get x to the fourth plus lower order terms. So we know this is actually going to rise on the left and rise on the right. Let's try to match that up with the crossing behavior on the functions. We know that it's going to bounce off of the -4, cross at the -1, and cross again at +1 before going back up and off into the wild blue yonder. Next, 3 zeros, x is 0, x is -6, and +5, corresponding to these terms respectively. The multiplicity of each is 2, 3, and 1, which tells us that it bounces, crosses, and crosses respectively. The leading coefficient, if I were to partially FOIL this out, would give me 8x squared times x to the third times x. So that would be 8x to the sixth power plus lower order terms. So combining this information about the long-term behavior, it's a positive even degree, and how this crosses at each one of these zeros, we can get a sketch of the graph. Let's mark the zeros at -6, 0, and +5. And we know that this is going to rise on both sides, and we know that it is going to bounce off this 0 at 0, but cross at the other two. So we're going to wind up with something that looks like the following graph. Let's apply this thought process to the next one. We have a 0 at -3, corresponding to this factor, at +6, corresponding to this one, and at -6, corresponding to this one. Their multiplicities are respectively 1, 2, and 2. And so we know that they cross, bounce, and bounce respectively. Now, what about the leading coefficient? Well, s of x is equal to 5 times what we would get if we expanded each of these and just gathered their leading terms, multiplying them together. That would give me an x squared from this one, an x squared from this one, and an x from this one, which would total up to x to the fifth. There's some other lower order terms. We don't care about those. We just want to mark our zeros at -6, -3, and +6. This has a positive leading coefficient, a odd degree, so it's going to come from this direction. And we know it bounces off this one, crosses at this one, bounces off this one, and continues on up, giving us the correct long-term behavior for a odd degree positive leading coefficient. Number 27 says a polynomial of degree 5 has the following characteristics: a leading coefficient of 1, a 0 of multiplicity 2 at x equals 7, a 0 of multiplicity 1 at x equals 1, and a 0 of multiplicity 2 at x equals 8. We know what factors corresponding to these zeros with these multiplicities will look like. This one is going to look like x minus 7 to the 2. This is going to look like x minus 1 to the 1, which we need not write. And this is going to be x minus 8 to the 2. Now, a polynomial that would satisfy these conditions is simply their product. If we multiply these all together, they will have the prerequisite zeros. Notice also that 2 plus 1 plus 2, the sum of the multiplicities, is the degree. We notice that its leading coefficient, if I were to expand this polynomial partially, would give me 1 times x to the fifth, and so on. So we really don't need anything else here. I would just like to note that in general, if we wanted to match this leading coefficient of being equal to 1, or have the polynomial pass through some given point, we would need to take into account the following indeterminacy. This polynomial information that I have braced here only tells me up to a constant multiple what my polynomial will look like. Notice that I could make c any number that I want, and we would still have the same real zeros with the same multiplicities. So in general, we'll be trying to figure out what is this coefficient c. And to do that, we're going to have to use the information like the leading coefficient has to be 1 or it passes through a certain point. The next ones ask for us to list all of the roots and their multiplicities. We must note the degree of the polynomial so that we can, again, establish that these odds and evens are in fact ones and twos, respectively. But once we've established that, this has a 2, this has a 1, the sum of those is 3. That's all the roots. And so, what is the root itself? Well, this is a -2, and this is a +3. So if I were to make a table of the roots versus their multiplicities, we would have a root at -2 of multiplicity 2 and a root at 3 of multiplicity 1. Here we have crossing, crossing, and crossing. There's crossing at every point. And we know that the sum of these things must add up to 3. And so ones are really our only option. Hence, we have the following roots and multiplicities. At -2, +4, and 5, we have our roots, and these all had multiplicity 1. This one appears to have degree 4, and we have 2 even multiplicities at these 2 roots, so they must be 2 and 2. If we made a table of roots versus multiplicities, we would have at -4 a multiplicity of 2, and at -1 a multiplicity of 2. Alrighty, that's going to do it for this video. Thank you very much for your patience. Have a great day. Good luck with your studies. I'll see you in the next one.